Hi everyone, welcome to these Python tutorials where we are putting special focus on image processing related tasks. Now in this video, let's talk about binary classification. In fact, a couple of videos ago, we looked at various types of machine learning related challenges, right? Various categories the machine learning related challenges fall into. And in the last video, we looked at regression. And from this video and on, we'll focus a bit on classification, starting with binary classification. And just to remind you, binary classification is where we are classifying an image, in this example, into one of two classes. So in this example, it's either infected or not infected. This image is infected. Or representing an infected cell. So here is another image. This is not infected. So this is binary. There are only two outcomes, either 0 or 1. 0 being, let's say, not infected, 1 being infected. Okay, so we're going to work with this data set. I'll show you, or I'll give you a link which is down here, where you can get this data set. And in fact, let's go ahead and click on this link to see what it looks like. So you're not surprised. Okay, so obviously there is some COVID information because this is from NIH, but when you go down here, this is what you want, cellimages.zip. Okay, and this one, I believe, has 13,000 images for infected and 13,000 images representing uninfected. But for this exercise, just to make sure things are finished in a decent time, I'm only going to work with 500 images that I have uploaded to my Google Drive account. So I saved them as part of my drive, Colab notebooks, data, and this one is cell images right there. Okay, so I copied the link to cell images, and that's what I called my directory, image directory down here. Okay, so let me close this part and let's continue from here. So starting with, again, this is a binary problem, so I'm not going to repeat that one more time. Now let's go down. This is because we added one. I think I changed this to infected, uninfected. Again, we'll come down and make more sense out of this code. So as usual, the libraries that we know we'll be using, I added them right away. So I'm going to use matplotlib and mpimage in case you want to format your pyplots. And from Keras, I'm going to use image data generator. Again, in case you plan on using, let's go down and see. In case you plan on using data generator, we are not going to use that, but I imported that in case you want to use data generator. Again, this is if you want to use data augmentation. I'm only working with 500 images, so I'm not going to use it. But if you have a lot of images, you may want to use data augmentation because you may want to only read 32 images at a time, fit the model and then load the next 32 and so on. We're going to use sequential method to define our model, and we define our model using convolution layers because we are working with images, and we are going to perform max pooling. Talked about this as part of my description of convolution layers, and batch normalization. And we'll also work with activation because we have to define an activation function, and dropout to make sure our model is not overfitting, and flatten, so we can flatten the two-dimensional convolutional outputs into one-dimensional vectors because our dense layers, or the neurons, they accept a flattened layer. So that's the explanation for these Keras libraries or methods that we are importing. And in addition to that, we are importing OS, so we can work with the file structure, CV to OpenCV to read images, Pillow to change image dimensions if we have to, and NumPy because these are all NumPy arrays. Okay, so here are the reasons. So I'm not sure if we ran this, but let's go ahead and run those lines. Okay, now let's define the image directory. I'm not reading the images yet. I just said this is my directory. And I'm defining a size of 150 because each image is different size. That doesn't work with NumPy arrays. We have to bring all images to the same size. So I'm going to resize all images to 150 by 150. That's the reason why I have this. And like I mentioned here, there are many ways to handle data, but the way I chose to do is by defining a empty list called dataset and empty list called label. I'm going to populate these two as we are reading images, which we'll do in the next part. So let's run this line. and move on to the next part. This part will be a bit slow, so let's go ahead and run this while while it's running, I'll explain this, because it's trying to read 500 images each for my images and for my parasited images and uninfected images. So while it's doing that, let me go ahead and explain this. Okay, parasitized images. These are the ones with these infections, right? I mean, so the directory for this, the images is os.lister. So I defined my base directory right there. So within that, I have, I mean, this may be self-explanatory, but it makes sense to show you. So within cell images, I have two folders, one parasitized, the other uninfected. And inside this, I have a whole bunch of images of parasitized and a whole bunch of images for uninfected. Okay, so that's why I defined the path to my folder right there. And for each image, what am I trying to do? If the image extension is PNG, which it is in this case, go ahead and get the image name and go ahead and read that file. Okay, so all I'm doing is go ahead and get the file name from this folder and then use OpenCV to read this. And you see, this is actually, we are importing this as color images with 3 channels. Okay, and then I am converting that into a pillow object. Why? Because it makes it easy for me to resize images working with pillow library. That's exactly why I imported from pillow image. This image can be used to resize it. So I'm resizing it to 150 by 150 right there. Okay, and once that's done, that specific image, I'm going to append it to my data set, which is nothing but this empty list over there. Okay, again, these are all probably basics to many of you, but it does help to go through these one line by line. So we are appending this as a NumPy array to my list called dataset. And while I'm doing that, I'm also appending the label, which is also an empty list, right, with a value of 1. So every image that I'm reading from this subdirectory called parasitized will have a label of value 1. And every image, similarly, that falls in this category, which is uninfected images, I'm labeling it a value of 0. So my uninfected images are 0, my infected images are 1 when it comes to label. This is how you can tag a label to your images. The other way to tag a label is just giving the label name. Okay, you can just say, okay, use the label name as your, the folder name, directory name as your label. If you have like 10 different subdirectories, you can just say, instead of writing them as 2 separate, you can just say, hey, go ahead and look through the folder or directory structure and use the directory name as the label and then just read the images. That's another way. But since I only have 2 subdirectories in this case, parasitized and uninfected, I just manually gave this a label value of 1 and label value of 0. If it's a text label, as you know, you need to just use label encoder to convert that into into 0, 1, 2, 3 values, right? Okay, so I've been talking for the last 3 minutes because I was waiting for this to be done, for this cell to be executed. But at the same time, I hope you learned something from that last couple of minutes. Okay, now let's go ahead and print the dataset shape. So we have 1,000 images, like I said, 500 images infected, 5 are parasitized, 500 images uninfected. So we have 1,000 images, each 150 by 150 by 3. By 3 because these are color images, RGB images. And our labels, we have 1,000 labels, and this is just 1,000 by 1, right? So that's the shape of this labels. Okay, so you're connected to GPU but not using, well, we'll use GPU in a minute, so please. Okay, now anytime I import any data where I'm importing the data or images and masks or labels separately, well, I'm not importing them separately. In this case, I'm assigning it. I like to print out and make sure it makes sense. That's exactly what we are trying to do right here. So here I'm importing random library. From random, I'm going to generate a random integer between 0 to the length of the data set. Let's put -1. Oh, sorry, wrong place. Oh. From 0 to length of the data set -1. And let's generate a random number and use that number in our data set to plot and also to label. So when I run this, it should show us an image and corresponding label. So the image is plain and the corresponding label is 0. And what is our 0 again? Our 0 is uninfected. Okay, so this is uninfected. It's very clean, so it does make sense. Let's look at the other one. This is also 0. This is also 0. This is also 0. I wonder if we'll ever see. Oh yeah, there you go. This is 1. Okay, which means it's parasited. So by the way, at the end of this, we talked about this. At the end of this, what I did is my data set is basically I think I should explain that. So here we are appending to our data set, we are appending all the images. It doesn't matter whether they're uninfected or parasitized. We are appending all of those, right? So that's why I'm looking for both images as part of our data set. So anyway, the sanity check makes sense right now. Again, I see these 2 parasites right there. So this label is 1, which is parasited. So I'm good for now. Let's move on to the next step. The next step is splitting our data into testing and training. All of these steps are exactly the same as the steps that we have taken in many of our previous videos where we looked at this type of deep learning structure. You read the data, you split the data, and there is a specific framework that we're trying to follow here. Okay, so we're splitting this into 20% test size, and remaining 80% would be the training size, which is our X-train. Now, if this is a normal structured data, in the last video we looked at regression, where we have like data going from 0.00 something to 600, for all the attributes. We scaled them, like using standard scaler or min-max scaler or normalize. You can use any of these. Because these are all images, 8-bit images, where values go between 0 to 255. The best way to scale them is just by dividing the pixel values by 255. That's exactly what we are doing here for both train and test. Alternatively, you can try this from Keras import normalize and go ahead and normalize the data. You can also try like min-max scaler and so on. All of those work, but this is the best, easiest one. Just divide this by 255, and this is very common when while you're working with images. Okay, so let's go ahead and do this. So our values are divided by 255. In fact, let's just make sure I'm not doing that 2 times. Okay. Now let's go ahead and define a model. Now what works best? I have no clue. Literally, I have no clue. All I know is that I need a few convolution layers, because what do convolution layers do? They apply convolution filters onto our images. So it's like generating features. So applying convolution filters is like generating features, and applying dense layers is like defining a classifier. Think of this as having a bunch of features and you have random forest classifier, right? So where do the features come from? They come from the convolution layers. In fact, except in this case, it's not just predefined features. These features are also learning. While you're training the algorithm, you're modifying the filters. Okay, that's what's unique with deep learning. So all I know is I need a few convolution layers and I need a dense layer, and my output needs to be 1 output. This is binary classification. And we are using sigmoid activation because this is binary classification. We talked about this many times. Many people think that, hey, this is binary, I need 2 outputs. No, you need 1 output because it's either 0 or 1. So if the value is close to 0, you know that this is uninfected. If the value is close to 1, you know this is parasitized. So you just need 1 output, right? So it's counterintuitive, but hopefully it makes sense. So all I know is I need some convolution layers, and I need at least 1 dense layer with certain number of neurons, and then the final layer. So let's engineer it this way. So let's say I have, let's spend some space here, a convolution layer right there with 32 filters, let's say, or features, and 3 by 3 kernel size. And what's the input to this? Coming from my input right there, right? So 150 by 150 by 3. That's my input shape. I also know I need an activation function for after each convolution layer, right? So an activation function in this case is ReLU activation. Again, we talked about this in our activation tutorial. Hidden layers use ReLU, especially with convolution layers. Okay, so ReLU, and then comes max pooling. 2 by 2. So usually when you define a convolution layer, these three go hand in hand. You have a convolution layer, you have an activation function, and then you have a max pooling. Maybe dropout, if you don't want to overfit your model, but we are not using dropout here yet. We're using dropout as part of the dense layer, but you can use dropout even here. Okay, so these three in the first block, and why 32? Again, you can experiment with 64 or 128, but don't go too broad and too deep. Then there's a good chance of overfitting. So let's start with 32. Let's add exactly the same one here again. Okay, so we are adding. In fact, you see, I also added something called Kernel Initializer as he uniform. Again, we talked about kernel initializers in the past, so let's not spend too much time talking about it. But this is almost identical to this one. And this is also pretty much identical to this, except instead of 32, I have 64 filters right there, okay, as part of my convolution layer. Okay, I'm done with 3 convolution. I think this is deep enough already. I don't want to make this any more deeper, otherwise the model will be overfitting. So next comes my dense layers, but what happens before dense layers cannot accept 2D arrays as input. It accepts only 1D vector. So I need to take this 2D and flatten it. So always between convolution and dense comes flatten. So we are flattening it. That flattened array is going into my dense layer with 64 neurons. Okay, and you can define activation and this in single line if you want, but I separated the activation as ReLU. Again, this is a hidden neuron, so ReLU. And then before I go to my output layer, I'm dropping out 50%. That's a significant amount of dropout. Maybe we can change this to 20% and see how that affects. But let's use this and see how our model looks like. Okay, and I added some notes saying that do not use softmax for binary classification, because binary classification means you got to use basically sigmoid, because softmax is used for mutually exclusive classes. Okay, either cat or dog, but not both. Go ahead and read this, and for binary sigmoid, that's it. Yeah, because you want a probability between 0 to 1, that's it. Now comes compiling the model. Again, this is a binary model. Did we run this? I think we did, but if not, let's go ahead and run it one more time. And next comes compiling this model. So how do we compile it? This is a binary example. This is again binary cross entropy, because this is binary. So that's the loss function. And for optimizer, again, we can try Adam, we can try stochastic gradient descent, we can do RMS prop, but let's just leave RMS prop for now. And what metrics do we want to follow as we are training the model? Well, let's follow accuracy. That makes the most sense for binary right now. And let's go ahead and print the summary of my model. Again, the input images would be 150 by 150 by 3, and then after the first convolution it would be 148 by 32, and then becomes 72, 72, 32, and so on, all the way down to 64, all the way down to 1. This is where we're getting our output. Okay, next comes training. That's it. Let's go ahead and run this for not too long, because we want to continue this video. So let's go ahead. It takes about looks like it's taking about 1 second or 35 seconds, I'm not sure, but let's do 20 epochs and see what we get. Okay, and while it's running, let's look at okay, we are giving X train, Y train, and batch size of 64, loading 64 images at a time during this training, and that means we have 20 epochs, right? So per epoch it's taking 64 as batch size. How many images do we have? 500. So what is 500 divided by 64? Whatever that value is, that many iterations it's going to take right now. Okay, we'll see that number in a minute. Again, we talked about this in one of the previous videos, so I hope you're following those videos because then this makes most sense. You see 13 out of 13. These 13 are number of iterations. So apparently if you divide your total number of images, oh, not 500 images, sorry. We have total 1000 images, and 20% we are saving for testing, which means we have 800 images for training. So 800 divided by 64, I guess, comes down to 13. But these are the 13 iterations it's taking. Okay, for 20 epochs. Now let's go down and have a look at what type of accuracy we get. So finally, I'm getting an accuracy of about 77%. Let's plot this. Let's plot how the curves look like. Yeah, it's still jumpy. This is nowhere enough for this problem. So let's increase this to 30, meaning if I'm running it again, that means it's 20 plus 30, right? So total 50 epochs, because it starts where it left off. It's not like it's starting from scratch. This is a problem if you're experimenting with this. If you really would like to start this from scratch, the easiest way to do is go to runtime and restart the runtime and then run it again, or restart and run all will take care of it. Okay, otherwise it's going to continue where it left off, meaning the last time it left off, the loss was this. The accuracy, remember, was 7.77 something. It started off right there. So as you can see, the accuracy is, well, it went down right there because it was probably took a wrong step. But anyway, it came down and now it went up to 82%. If I plot this, it may look a bit weird because it's not plotting from 0th epoch all the way, but it's okay. It's not looking bad. Okay, now is the time to test the model. That's it. I mean, this is literally very similar to a regression or whatever. Once you put the model, then construct your model, train it, then the steps were very similar actually. So now let's go ahead and generate a random number between 0 to how many ever test data points we have, and I'm just showing the image and also showing the original, our prediction and the original label for this image. So just a few tests. So this one, our prediction, again, our predictions, we are using sigmoid, right? That means it gives us probabilities. And here, the probability for this being a parasitic is like 0.999, and this is 1, right? I mean, this is our label, original label. So that's obviously doing a great job there. So let's see if there are any ambiguous ones. This one also, 0, original label, we got 0.00064. If we set a threshold saying that everything below 0.5 probability, convert that into 0, anything above 0.5, convert that to 1, then this becomes a classification instead of probabilities right there. We'll do that in a second. So now let's go ahead, and here you see this one has a probability of, or the value output is 0.62, but our actual value is 1. That means it's not highly confident that this is a parasitid, but it is. If we set a threshold of 0.5, we'll get the right answer. Okay, so let's run a couple more, 0.74 and 1. So that's not bad. This is 10 to the minus 5 and 0. It seems to be doing great with the uninfected ones and not so great with parasitid, even though it's doing a good job with the parasitid ones. Okay, so I think we have seen enough of these. This one has a 1.0. That's great. Okay, now let's go down and print out the accuracy. This is pretty straightforward. We are getting 82% of accuracy, okay, based on all of our testing images. And again, the way you do that is model.evaluate, and then what are we evaluating? Our X test and Y test, right? So you give your X test. So in the background, it actually does the prediction and compares it against Y test, and it gives us two things. One is the loss, the other one is accuracy. I chose not to print loss, but I'm choosing to print the accuracy, okay, in case you wonder what's happening here. Okay. Now, how do we know how is it doing for parasitid versus uninfected? We already noticed that it's actually doing a better job with uninfected versus parasitid. But is that true? Or is it just the random nature of the way I chose to look at these images? So this is where confusion matrix, again, we talked about this a couple of videos ago. What is confusion matrix? What is ROC and AUC? We're going to use that now. That information. So first of all, let's print the confusion matrix. To print the confusion matrix, you need classification, not probabilities, because your confusion matrix is basically comparing your predictions with your true. Our true values are binary, 0 or 1. So we have to make our predictions binary. So how do we do that? You set a threshold. Like I said, let's set a threshold of 0.5. Logically, it makes sense, right? And then from scikit-learn metrics, get your confusion matrix and do your prediction, right? How do we do our prediction? Model.predict X test. If you just do model.predict, you're going to get probabilities. So I say, okay, you get a probability. If it's greater than or equal to my threshold of 0.5, okay, then that is my prediction. And then we can do our confusion matrix and plot it. So let's go ahead and run these to have a quick look at our confusion matrix plot. This is not good. You can see why we are getting only 88% or something, because 92 true positives, 72 true negatives. That means 92 images, uninfected images, are truly labeled as uninfected. 72 infected images or parasited images are truly labeled as infected. 26 of these parasited images are falsely labeled as uninfected, and the other way around here, right? Now the question is this because the model is not doing a great job, or is this because my threshold that I set here is not appropriate? Of course, you can get your model even better, so your probabilities are even better. Yeah, that's something you can do. All of that information is reflected by your ROC curves. We talked about this, and how do we print our ROC? So from scikit-learn metrics, you can import ROC. I think there is another library which I'll make another video in future with better ROC curves, but this one actually works great. So from scikit-learn metrics, get import ROC curve, and go ahead and predict your, do your Y predictions, and then apply your ROC curve onto your test, and then the predictions, just like confusion matrix. We are doing very similar to confusion matrix, and what it outputs is false positive, true positive, and thresholds. All I'm doing is just plotting this. That's it. I'm just plotting false positive and true positive rate, right? That's what ROC curve is. So let's go ahead and plot that. So there you go. This is our ROC curve. Okay, I'm not looking at the thresholds right now. In fact, the best way to do this is plot this and also plot the threshold values, so you know exactly what that threshold value is right there. Why? Because this is the point where you get the best, the model, right? The best model is vertical and horizontal right there. So this model is not bad, actually. It's not close to random. It's much better than random. And the best threshold that gives us the best split between these true positives and false positives is the one that's closest to this corner, which is probably that data point. How do I know that? This is 0.8 something. Well, there is an easy way to find that out, okay? So let's go ahead and just run these lines of code. Again, this is pretty straightforward. I have the explanation here, and this gives us a optimal cutoff between, these two. So all I'm doing is looking at my true positive, false positives, and then printing out the ideal threshold value right here. So the ideal threshold is 0.1432. So this is saying that based on this, my ideal threshold is 0.1432. I'm a bit surprised with that, but let's see if that makes sense. 0.14, right? So let's go here and say 0.1432, and let's print out our confusion matrix. Yeah, that's not bad. I get 85, 80, and a good balance between these two. You see, if I go anywhere, if I go to 0.05, then one of these will go up, the other one will go down. You see, this one went down, that one went up. And if I move it the other way around, 0.5, then this goes up and that goes down. In fact, the best thing to do is go and get my model correct. Okay, so 0.1432. I think was the one where it's giving us the best split between these two. That's the best compromise if you cannot change the model. In this case, I recommend going back and removing probably or training for a longer time, or modifying the model such a way that you add I'm thinking about what would maybe adding a dropout layer generalizes the model a bit better, but I am not seeing like a strong overfitting here. So maybe adding another or removing actually a convolution layer can also help. Again, these are the things hopefully you can experiment with. Okay, but this is fine. 89% is not bad. Yeah, is not bad, but I think you can get up to 95 to 98% on this type of data sets anyway. Okay, so one final thing, how good is this model? Again, area under this curve can really tell you how another metric, in terms of how good the model is. And Scikit-learn metrics has AUC. You just need to import that. So 91% chance that I can separate between true positive and true negative. That's what this basically means. So this is not bad, but I think this can get even better. So again, that's an exercise. I'll leave it to you, but I hope now you understand binary classification. Again, most examples, you can follow this. Let's say you are getting a whole bunch of images from your microscope. Some are good, some are bad, what you think as bad. And you're like, hey, I don't want this. I want to build a filter to my image analysis pipeline where I would filter out the bad ones automatically and only the good ones go through your image analysis pipeline, right? So that's a binary classifier you're trying to build, good versus bad. Just train it on a whole bunch of what you think are good images and bad images, and then it usually does a great job, like 95+% in terms of sorting these images. And we have done that. That's why I'm mentioning that application to you guys. Okay, thank you very much. In the next video, let's look at multi-class classification. Until then, please subscribe to this video and like this video, and let's meet in the next tutorial. Thank you.